Hi, kiddos. So just like the last video, you're going to want, well, you might want this worksheet in front of you. There's just a lot of word problems, so I didn't feel like handwriting them out while I was in a video. That seems dumb. So the front page of this are, here, air quotes, this is what we're doing in class. And then the back page is where you'll find the homework for this night. Again, I guess you don't really need to print it. It's just whatever you want to do. But it lives in OneNote in Content Library. It also lives on Canvas if you want to download it there and print it. So here we go. We are talking related rates today. So rates, those are derivatives, and they're going to be related to each other, is essentially what's happening. So what's going on? Let's read number one. A point is moving on the hyperbola. Don't panic. You don't have to graph it or know anything about it. What is the rate of change of y when dx dt is a half and x equals 1, y equals negative 2? So here's the question. I mean, I just told you didn't have to graph it, and you don't, but I just want to show you. So here's a hyperbola. Oh my gosh, that's good. All they're saying is when you're sitting at this point, 1, negative 2, which I choose to put right here, and this point is moving. So it's moving on the hyperbola. So maybe it's traveling this direction. In fact, I know it is. So if it's traveling this direction, they want to know how is your y value changing when your x value is changing at 1 for every 2 time. So there's 3 variables here. There's an x and a y because you're on a point on the grid, but then time is passing. So time is another variable. Okay, so we have this equation for our hyperbola, y squared minus 2x squared equals 2. And then this is going to give you a clue about how to take this derivative. We're going to go take the derivative of this equation with respect to t. Okay, well, that's new. Well, I guess that's not new because you've done parametric derivatives, and so having d dt is not new. And you've also done implicit differentiation. So differentiating with respect to a variable when you have 2 of them in your problem shouldn't be too weird. So this is kind of like a combination of things you've already done. But we're going to go take the derivative with respect to t of both sides. Don't worry, I'll help over here. But then on the left-hand side, you have to remember that y is changing in this problem. Y is not constant. The y value of that point is not constant. So y is a function of time. Y is changing over time. Same with x. They're both changing. So when I do my super fun power rule on y squared and I pull the power, subtract 1, I have to multiply by dy dt because that's what implicit differentiation tells me to do. That's chain rule. But I have to do the same thing here. So this will be minus 4x dx dt. So that was implicit differentiation with 2 chains. And the reason we have to do those chain rules is because x and y are both functions of time. X and y are both changing over time. All right, that's the new part of this. Everything else is plug and chug. Because if you've done a good job, you should have everything you need with one thing that you're looking for. So dx dt is a half, x is that, y is that, and they're asking me for the rate of change of y. They're asking me for dy dt. That's the rate of change. That's the slope of y. So if I plug in what I know, I'm going to have 2 times negative 2. dy dt is the question. Minus 4 times 1 times a half equals 0. And then it's a quick clean to say negative 4 dy dt's minus 2 is 0. Add the 2, divide by negative 4 dy dt is negative 1/2. Sorry for the super awkward splice, but I wrote an 8 instead of a 4, and I'm super embarrassed. Now back to the original. So if I plug in what I know, I've got 2 times negative 4 times dy dt, or you could solve for dy dt first, whatever you want to do. This is me just plugging in all my information, and then I'm going to solve it, and I'm going to clean it, and it's not going to be so bad. Oops, minus. So I'm going to add that over and divide by 8, and I get that dy dt is 1/4. So y is changing at 1/4 when x is changing at 1/2. All right, let's look at the next one. An edge of a cube is increasing at a constant rate of 2 inches per second. Do you hear the rate in that? 2 inches per second. Inches per second. So just like in those verbalizations we did late last week, that's a derivative. That's a slope. How fast is the volume increasing when x, the length of an edge, is 5 inches long? So that each edge of a cube is increasing constant rate. So they're calling the edge x. And if they tell you that the edge is increasing at this rate, I'm going to call it dx dt. So the first question was really friendly because they gave me all the notation. This one's not as friendly because I have to go find the notation myself. The other thing they tell me is that they want to know what's going on when x is 5. This is an instant in time piece of information. That's not a forever piece of information. This cube is growing. So the edges are not always 5 inches long. It's just they want to know how is the volume changing at that instant. So this is not something I'm going to use until after I've taken a derivative, and then I can plug it in. Okay, what are we going to differentiate? Well, you're going to have to dig just a little bit in your words, but they're asking about volume of a cube. Well, I took geometry once. That's how I find volume of a cube. How do I know what to differentiate with respect to? I've got to go back and read. So it says per second. That's a time value. It means we're going to go differentiate both sides with respect to time. So the left-hand side is super simple, dv dt, which is what they're asking you for. How fast is the volume increasing? That's the rate of change of volume over time. Equals pole of power, subtract 1. X is a function of time, so I have a dx dt. X is changing. Now that I've taken a derivative, I am living at an instant in time, and I can use this instant in time information. So I'm just going to plug everything in. This is 3 times 25 times 2, and that is 150. 150 what? So this is dv dt. You can read this side of your equation to help you with the units. How is volume being measured? Well, if the side lengths are measured in inches, the volume must be inches cubed. Over how is time being measured? Second. So that volume is changing at a rate of 150 cubic inches per second. Okay, number 3. Hey, at some point you might want to pause and go see which of these in the homeworks feel comfortable to you and that you're ready to start. Maybe none yet. I understand. This is weird. Number 3, sand spills to form a conical. That's a fancy way to say a cone. So we're making a cone with height equal to radius of the base. So I'm going to call this R. I'm going to call this height. How fast is the height increasing when the height is 3 and sand is being added at the rate of 2 cubic feet per minute? All right, let's finish dissecting the words here. So I drew a super great picture, and that took me through here. But now it says, how fast is the height increasing? Increasing is a derivative word because it's talking about a slope. So if they're asking about height increasing, the question is about dh dt. How do I know it's dt? Because things change over time. If they wanted something more specific, they'd have to say. So that's what I'm looking for. And they want it at the instant in time that the height is 3. Oh, and also I have this 2 cubic feet per minute. They say that that's how fast sand is being added, and that's great. But in this problem, it's important to know that the way sand is being added and the units on this cubic feet, that's a volume measurement. Same reason that this cubic inches was volume. Per minute, oh, that's time. So they've given me dv dt. They've given me the change in volume over time. Okay, Now I'm going to look at what I've got and figure out what I need to set up, because they never specifically said, and in number 2, they specifically said about volume increasing. So I need to come up with, in my little brain, some equation that I can differentiate both sides of that has volume and has height in it. Well, lucky for me, I took geometry once, and I know the volume of a cone is 1/3 pi r squared h. And I feel like this is maybe a good idea because I have dHdt, and so I have an h, and I have dVdt, and I've got v, so that feels like maybe I'm doing the right thing. But I don't really want to go in right this second from the very beginning and take a derivative yet, because over here, I'd have a product rule to do. This radius is growing. The radius is not constant. And then over here, h is growing. H is not constant. So I'd have to do a product rule. And then I'd have things in my derivative that I wouldn't have values for. And that makes me nervous. So I'm not ready to differentiate yet. So the one piece of information we haven't addressed is that height equals radius. So, okay, no big deal. R and H are the same thing. So let me just go replace all my R's with H's or all my H's with R's. And it matters which one you choose. I'm going to choose to replace all my R's with H's because I want to make sure I have an H in my derivative after I've taken my derivative. So I'm going to use this version of volume. I'm going to make it pi over 3 just to keep all my constants together. This would be h squared. H squared times another h makes an h cube. And now I'm ready to take a derivative, both sides, with respect to time. And now I've got dv dt equals pi over 3 is a constant, so it's just a coefficient living right there, and it's very happy. Leave it alone. But I still need to pull a power. So I have pi over 3, pull a power, subtract 1 times dh dt, because h is a function of time. And if I've done good, I should have everything I need. So dv dt was given in the question. They're telling me h is 3, and dh dt is the thing I'm looking for. So we did a good job. The rest of it is a plug and chug and a solve. So let's see here. dv is 2. I'm going to cancel these 3's. Here's a pi. H is 3 squared is 9. H. So that gives me dh dt to be 2 over 9 pi. And the units on my answer, I can read from over here. The height of that cone has got to be measured in feet. And the time for this problem is being measured in minutes. So it's 2 over 9 pi feet per minute. Okay, one more. I know this is a long video. I'm really sorry. You can always pause and come back. Although you're this deep now, why not finish? A boat is being hauled towards a pier, which is 20 feet above the water. I think I need to draw a boat. Well, this kind of gives it away, but I know it's coming. There's my boat. Here's my pier. This is 20 feet. It's wildly out of scale. They didn't say what kind of boat it is. Maybe it's a toddler play boat for the bathtub. Who cares? This is your rope. I'm going to use R for rope. I'm going to use X because in my mathematical brain, anything that's horizontal is X, and this is Y. But they already told me that was 20. This 20 is constant. So I put it on my diagram. I only put things that are constants on my diagram, like things that aren't changing over time. Like I don't think the pier is shrinking and growing over time. So it's 20 always. All right, information. The rope is being pulled in at a rate of 6 feet per second. So I called it rope. I called it R for rope. So now I know dr dt is 6. How fast is the boat approaching the pier? Remember, this is the pier. So if I want to know how fast the boat is going that way, then the question is asking about dx dt. And it's asking about dx dt at the instant in time when there's 20 feet of rope at r equals, or 25 feet of rope. That doesn't look like enough information for all of the letters that I have drawn in my really great boat picture over there. But do you see some kind of relationship that you can set up that will include R and X? I mean, you should see, let's see, 6, 12, I count 13 relationships you could set up. Because remember, like you took trig once, you could make an angle in here and you could use all 6 of your trig functions, which means you could use all 6 of your inverse trig functions. But those, while true, are not helpful because you don't know anything about the way that angle's changing. So I'm just going to erase that because you're panicked anyway. I think the relationship we should set up is x squared plus y squared equals r squared. Hey, Pythagoras. All right. The one thing I'm going to do before we take our derivative is remind you again that this 20 is always 20. So there's no reason to confuse yourself with thinking that this is a function of time and then worrying about its derivative. We're just going to put 20 there. So the equation that we're going to differentiate is this. Yes, I know what 20 squared is, but remember, it doesn't matter. We're going to go take a derivative. It's a constant. All right, here we go. We're going to pull a power, subtract 1, dx dt. Derivative of a constant is 0. Pull a power, subtract 1, dr dt. And now I should have everything I need. Let's see. Dx dt is what I'm looking for, so it's okay that I don't know that. R was given, dr dt was given. Oh no, I don't have x. Okay, well remember that this is your triangle. This is your always triangle. It's your forever triangle. It's your infinity triangle. But at this instant in time, we know more. This is always 20. At the instant in time, this is 25. Can you find x if you know 2 side lengths of a right triangle? You better. Remember 3, 4, 5 triangles are a thing. This is 15. So I'm going to use that for x. The other thing I'm going to do to make my algebra super fast is cancel my 2's, reduce my 2's, don't tell pickle. Let's see, x is 15, dx dt is what I'm looking for. R is 25, dr dt is 6. I don't have a calculator. I did not work these out ahead of time. So I'm going to clean in real time. You get to see this. I always think of these as like 3 times 5 so that I can do, oh, look, 5 cancels with one of those, 3 cancels with one of those. That's 10. I never multiply out numbers until I've canceled all my primes or all my factors because I don't like to make numbers bigger than my little brain can manage. Anywho, let's take a look at units on this. X is this side length, and lengths were being measured in feet in this question. Time was being measured in seconds in this question. So the boat is approaching the pier at 10 feet per second. That seems awfully fast. Good thing it's a tiny little boat so it doesn't smash the pier. All right, here's the thing about related rates. Once you figure out what to differentiate, it's this, in my opinion, that's the struggle eventually. The first struggle is figuring out how to label your information. I know that. The second struggle is figuring out what to take the derivative of. Once you have that, you're fine. I think you're fine. You're usually fine. But it's going to take you a couple days to get there. So the other thing about related rates is there's nothing else for me to teach you. We just need to practice it. And I think I've given us 3 days of pure practice. So you may or may not have more videos coming. I might work through a question on a video, but it won't be new information. It'll just be practice of, I need to stop this video. It's going so long. Oh my gosh, let me know if you need anything. So if I plug in what I know, I'm going to have 2 times negative 2 dy dt is the question, minus 4 times 1 times a half equals 0. And then it's a quick clean to say negative 4 dy dt's. Minus 2 is 0. Add the 2, divide by negative 4 dy dt is negative 1/2. Sorry for the super awkward splice, but I wrote an 8 instead of a 4, and I'm super embarrassed. Now back to the original.